Welcome back, everyone. In this video, I'll be going over the limit laws lecture. Now, to start off with limit laws, there are a lot of limit laws, and I wanted to pre-write them down. And what I really want to do is talk about what they're saying, because ultimately, when we put all of these limit laws together, it's going to give us a really nice result. And we'll see why it's so nice after we work a couple problems as well. So first off, the setup here says let A and C be real numbers. No i's are allowed. It lets n be a positive integer. So it's just a positive whole number like 1, 2, 3, 4, so on. And let f and g be functions with the following limits. So the limit as x goes to c of f of x equals L. And the limit as x goes to c of g of x equals k. So you can just remember the important setup here is that we're taking the limit as we go to the same value for each function, c for each case, and then the one for f of x is L and g of x is k. Now I want to go over what all these properties mean, and I broke them down into 3 parts because really you think about them separately. I'll turn your attention to the base properties first. The base properties are basically the main properties. When you combine base properties with the other 6 rules here, so the 5 main properties and the 1 function composition property, it's going to tell you everything. But if you didn't know these base properties, these are honestly kind of useless. So we do need to know the base properties. Now what the base property says is the following. It says the limit as x goes to c of the function a, so it's just a number, imagine 2 or something. No matter what you're plugging in for c, what you're taking the limit is, you always get out the 2. Now, why does that make sense? Well, once again, I'll graph here to explain it. And I want to go ahead and pretend a is 2. So we're looking at the graph of y equals 2. Let me go ahead and just zoom out so you can see the x-axis and everything. This is the line y equals 2. And what we know about limits from their graphs is that if we pick, say, x equals 2, which is right here, what is the limit as x goes to 2? Well, we think about walking towards it from the left. Well, we're always at the line y equals 2, so it's always there. And what if we come at it from the right as well? We're still at y equals 2. But the x value of 2 is not special. I could have done it at 4, I could have done it at 5, or anything. So no matter what x value I pick, the limit is always 2. And that's exactly what this base property is telling you, is that if you take the limit of just a number, it doesn't matter what your limit value is as far as x, what you're plugging in, you always get that number out. Now, what about the second one here? The second one is saying specifically if you do the limit as x goes to c of the function x, then you get out c. It looks like you're just plugging in c. And that's really the way you're going to want to think about it. Whenever you see just an x, you plug in c. So let's go ahead and see why that is true. I'm going to graph y equals x this time. And I'm just going to pick a value like I did before. Let's pretend c was 1. When c is 1, we can trace up to our graph that the y value is also 1. Now, is the limit equal to 1? It certainly looks like it, and it is, because as we come towards x equals 1 from the left, let's pretend we're walking on this side, the y value is going towards that 1. As we come from the right, the same idea is happening. As we come from the right towards x equals 1, the y value is also going to x equals 1. But 1, again, is not a special value. If I go to 3, you can see that the y value is 3, and it's definitely the limit as well because the graph's all connected. We walk towards the same spot from the left and right. -2, same thing. And if I pick any x value, the y value is going to be the limit, and it's going to be the same thing because it's the graph of y equals to x. So what this property is saying is that if we have just x, visualize doing the limit by just plugging in c value. Right, so those 2 properties really give you the entire of the main properties in function composition. It gives it something to make sense. Now, the main properties and the function composition properties are not about specific functions that are just numbers and an x. It's going to be about general functions. So the first property here, scalar multiplication, it says if you're multiplying a function by a number, so a times f of x, and you want to do the limit, what you can do is just bring the a outside of the limit. So visually, what you want to notice here, let me not use purple, I'll use green. Kind of to go from this part of the equal sign to this one, I took the a and I brought it out. That's visually what I was doing. And if you take the a and bring it out, it looks exactly like this. And we know the limit of f of x as x goes to c is L. So we get a times L. The way I think about it is if I'm multiplying a function by a number, I can do the limit and then just multiply the limit by that number. That's what scalar multiplication tells you. Addition and subtraction, I'd like to just throw them in at once because they are pretty much exactly the same. If you're adding or subtracting the two functions, f of x plus g of x or f of x minus g of x, you can split up the limit and you can do the limit of each part. So we can do the limit as x goes to c of f of x, and then plus or minus whichever one your equation is, and then the limit as x goes to c of g of x. And we called the limit of this one L and this one K, so it's L plus or minus whichever one you're doing, K. The easiest way to think about this one, when you're adding or subtracting limits, you just do the limit of each part and then you add or subtract the numbers. Multiplication pretty much works the same way as addition or subtraction, except you're multiplying here. So if we multiply f of x times g of x and we want to do the limit, then we multiply doing the limit of each, which is what this portion here is saying, and we just get the result L times K. And then the one below that, division is the same exact way, except division, of course, is written differently. But if we do f of x divided by g of x, and then we do that limit, what it's saying is you can do the limit of each part, pretty much like all the rest of these properties say. And then it equals the limit of f of x as x goes to c, which is L, and over the limit as x goes to c of g of x, which is K. Now the last one I have here, you could write a whole bunch of these main properties, but these 5 really bring everything together. The exponents. So if you take your function f of x and you raise it to the n power, remember n is a positive integer, so 1, not insightful, but 2, 3, 4, anything. What it's saying is you can bring the limit inside. So notice here the limit came from the outside. I went inside. And then the limit as x goes to c of f of x is L. So this is L to the n power. Once again, kind of think about it the same way. You're basically just figuring out the limit and then doing whatever the operation is. Exponents, multiplication, division, addition, subtraction, or multiplying by a number. Now the last property we've got here is called the function composition property. And I know these are a lot of properties before we start talking about the problems, but it's really going to help us get through the entirety of the section. And we do have to talk about all of them. So the function composition property, it says that if the limit as x goes to c of f of x equals L, and the limit as g of x, the limit as x goes to L of g of x equals K, notice I used a different letter here. I didn't use C for both. I'll explain that in a second. Then what's happening, it says the limit as x goes to c of g of f of x equals K. What does this mean? Why is this so important? Well, what this is really telling you, and this is something you definitely want to write down, is it's going to tell you you can bring the limit inside of a function. We do have to make the assumption the limit exists. If it doesn't, then this doesn't really work. But for the most part, all of our functions, we're going to have limits except for some specific examples. And I wanted to do this with a very specific example. This is really helpful when you do limits with trig functions, exponential, logarithms, inverse trig functions, you name it. Pretty much anything that's not just powers of x. Very useful. So let's say we wanted to do the limit as x goes to 2 of sine of x squared. Well, if you look at all the rules we have up here, you can't actually use any of the rules from the main properties or the base properties. Why? Because this isn't multiplication, this isn't division, this isn't addition, this isn't subtraction, it's not scalar multiplication. You do have an exponent, but the problem is the exponent's inside of the sign. But what this function composition is telling you is that I can move this limit inside. And what it's saying is I can take the sign, leave it on the outside, move the limit inside, and then it's saying do sine of the limit as x goes to 2 of x squared. And what this is, how we would evaluate this is really what the section's about, but it's going to pretty much boil down to one thing. You're going to plug in x. Why? Well, your exponent property says you can do the limit of the exponent, meaning I'm going to rewrite this sign on the outside. I can move this exponent, quote unquote, outside the limit, meaning, and we won't usually go through this much detail just to do this, but just to explain it, we do the limit as x goes to 2 of x, and then we square it. But notice it's still in the sign. The reason I have to do it like this is I only know how to evaluate the limits using these two base properties. If the limit is very literally a number or just x. This is x squared, so I had to just use the exponent rule to say I can move the exponent outside and I can do the limit as just x. And then we know when we have the limit of just x, we plug in the 2. So this is sine, and the entire inside here without the exponent, using our property 2 up here, it says that this is just 2. Right? We have the same exact setup here with c equals 2, so this is 2. We still have that squared power on the outside, so we got to square it. And then 2 squared is 4, so this equals sine of 4. And whatever sine of 4 is, not a big deal. But the point here, and the point we're going to see throughout the section, is that when you have to do a limit, it's pretty much just going to look like plugging in the number. There are going to be some exceptions, but it's going to look like plugging in the number. And think about it. If I told you at the beginning to do this limit, and the only piece of advice I offered you was plug in the number, what would you get? Well, if you just plug in 2, for x, you get 2 squared, which is 4, and you get sine of 4. That's exactly what we got. All these rules together are pretty much going to tell us plug in the number. There's just going to be some exceptions to that, which we'll see in the later part of the section. All right, but before we get to specific examples, you really do want to make sure you understand how to use the properties, because when we move on throughout the class, when we hit the big topic of derivatives, we're not going to have all the same properties, and you don't want to get confused. And if you practice the limit properties now, hopefully you'll remember they are the limit properties. They are not going to be the derivative properties. And just want to get some extra practice. All right, so number 1, it says, given that the limit as x goes to 3 of f of x is 3, the limit as x goes to 3 of g of x is -1, and the limit as x goes to 3 of h of x equals 0, evaluate the following. Right? Well, what's very important is that you can't actually ever plug in a number here because we don't know what f of x is. We don't know if we can even figure out f of 3. But what our limit properties say above is that if we have add or subtraction, which we do, we have subtraction, then do the limit of each part. Once again, I'm doing these in the very brutal detail you would have to be following all the properties. So we got the limit that was supposed to be a minus sign, the limit as x goes to 3 of f of x. We're just distributing the limit through, minus the limit as x goes to 3 of 3 times g of x. Now the idea here is we only want things like this. We only want the limit as x goes to 3 of f of x, which is what we have. This equals 3, so we can plug that in. But the other one isn't quite there yet because we don't know the limit as x goes to 3 of 3 times g of x. We only know the limit as x goes to 3 of g of x. So how are we going to get exactly that? Well, luckily we had that first scalar multiplication property that said if you have a number inside, you can move it out. And that's what we're going to do. Okay, so the first thing is 3. I'm going to go ahead and plug that in because we just figured out that that's 3. And then we have minus, and I'm taking out the 3 here. And then I still have the limit as x goes to 3 of g of x. So, notice what's right here. And when I take the 3 out, I'm still left with the limit as x goes to 3 of g of x. But now that's exactly what I have underlined in blue above. And this equals -1. So I can plug in -1 here. And we get, I'll keep it color coded for this first one so it's easy to see. 3 minus the 3. And then we're plugging in -1. So times -1. And then you can just simplify that number. 3 times -1 is -3. So the double minus is a plus. 3 plus 3 is 6. Now, if you get, really practice these and get good at them, you can probably figure this out right away. You might say, oh, this is going to be 3, this is going to be -1, and I can just plug it in. That's the idea. The idea is you're plugging in the entire limit, though. You're not plugging in x to the function. If you do that, you are very wrong, even though you might come out with the right answer. All right, number 2, just want to practice more of our rules. We've got the limit as x goes to 3 of the square root of f of x over g of x. Now, the first thing you notice here is there's a fraction bar. We are dividing. That means we can use the rule that says we can do the limit as x goes to 3 of the top, square root of f of x, over the limit as x goes to 3 of the bottom, which is g of x. Right. Now, how are we going to do the top? We should know just from the above example, we know the bottom is -1 already because that's exactly what we have here. So let's go ahead and just plug in -1. But what about the top? You don't have a rule for radicals. You have a rule for exponents, but they have to be whole numbers. This is where the function composition comes in. The function composition is going to tell you if you have a square root, a radical. It doesn't matter what it is. It could be like a cube root, which we don't actually have there. But any radical, if we have a trig function, if we have an exponential function, if we have a logarithm, we just bring the limit inside. We get the square root of the limit as x goes to 3 of f of x. And we know that inside is 3 because that's exactly what we got there. The limit as x goes to 3 of f of x equals 3. So we're going to have the 3 inside the square root. And then we have that -1 on the bottom. And you simplify that, this just equals the negative square root of 3. Now, one thing you might think of is that if we had brought this inside and we got and this was a negative number, so we would have a negative square root, then it's D and E because we're not going to deal with complex numbers. All right, number 3. One more just to practice these. We have the limit as x goes to 3 of h of x times g of x, and that's all to the 4th power. This is an exponent, so we can use the exponent rule. It says bring the limit inside, so we can do the limit as x goes to 3 of h of x times g of x to the 4th. Now keep in mind that this limit is multiplied to everything, so it's getting multiplied to the h of x and g of x. And our multiplication rule says do the limit of each one and multiply. So we've got the limit as x goes to 3 of h of x times the limit as x goes to 3 of g of x to the 4th. And now we can plug in each one of these. We haven't done h of x, so I'll scroll up here. The limit as x goes to 3 of h of x actually equals 0. So this is 0. The limit as x goes to 3 of g of x equals -1. 0 times -1 is 0. And then to the 4th power is still 0. So this limit is just 0. Right. But that should be a good rundown of using these properties. One thing I want to mention, and I mentioned it throughout. If you notice really what we're doing, we're kind of just plugging in some ways. We know the limit of h of x as it goes to 3 is 0. We know the limit of g of x as x goes to 3 was -1, because that's what we're given. And it looks like we're just plugging it in. 0 times -1, and then to the 4th power on the outside. And same thing for number 2 and 1. And that really is the idea with these properties of limits, is it's ultimately telling you plug in the number and see what happens. So I'm actually going to stop the section right here, and I'll make a new video for the rest of the section so it doesn't get too long, but this is a really good start.